In this video, we are going to be looking at chemical versus physical changes. So first, let us remind ourselves that when you study grade 9, we have this concept of physical and chemical change. Like, for example, what happens to the composition of paper when it is cut into smaller pieces? Does the paper turn into another material? And then what happens to the sugar granule when it is dissolved in water? Do they turn into another material? How about the water? Does the water turn into another material during the process? Explain. Obviously, by now you should know that the answer to both of these questions is no. The paper still remains paper, albeit now very small because you've cut it into pieces. And the sugar and the water are just mixed together, but they are still essentially sugar and water molecules. They did not change into another material, right? So, a physical change here results from changing the form of a material or substance. So, this is important, the form. So, in other words, only the form is changed, not the chemical composition. So, for example, if you have liquid water, like here, let me direct your attention to here. This is liquid water, right? So you have those particles. And then when you heat that liquid water and it becomes gaseous, it becomes steam. Notice that it's still the same particles. It's still made up of water particles, but now the particles are more energetic and they are farther apart from each other. But if you look at each individual water molecule, it's still a water molecule. There is no change there. Now, in contrast, a chemical change involves the rearrangement of atoms of a material, which effectively changes the compositions of the substances involved. So that means, for example, here you have an illustration of hydrogen gas, right? Two molecules of hydrogen gas. It reacts with oxygen. And then now, if you can imagine these atoms rearranged, and now instead of hydrogen bonding to hydrogen and oxygen bonding to oxygen, now we now have one oxygen atom bonding with two hydrogen atoms forming water. Okay, so take note that this would not happen if they did not do certain steps. And what are those certain steps? Well, number one, there must be some sort of breaking of the bonds between the atoms of the original substances, right? If the hydrogen did not break bond with the other hydrogen, it would not be able to form water. And then after that, there is a rearrangement of atoms into new configurations, meaning new proportions. Instead of one hydrogen to one hydrogen and one oxygen to one oxygen, now it's one oxygen to two hydrogen atoms. And then finally, you have the formation of new bonds. Okay? So again, just to make that clear, let's go back to our illustration here. You have the original substances. They have to break their bonds. They have to rearrange into new configuration, and they have to form new bonds. So that's a chemical change. Notice that's very different from a physical change, because when you have a physical change, again, the bonds between the atoms of paper or the bonds between the atoms of the sugar and the water, they did not really have to break, and the atoms were not really rearranged. It's just the physical form, the phase, and other types of physical forms. That's the only thing that is changed in a physical change. But in a chemical change, again, there's this elaborate process where you come up with new substances, and it's very different from the original substances that you originally had. Okay, so the problem with this definition is this is very subatomic, or at a very uh, in-depth zoom. Sir, I don't have eyes that can see if the bonds of the materials that I'm dealing with are actually breaking and forming into new substances, right? So, yes, understandably, that is the case. And so, what we do is we look for evidences. So, these evidences are things that we can see in the real world. Okay? These are things that we can see in the real world, and they manifest what we have been talking about, which is the breaking of the bonds, the rearranging to new configurations, and then the formation of new bonds. Okay, so what are these evidences? So there are 5 of them. So number 1 is production of light. So a lot of chemical reactions produce light as a byproduct. So for example, when you um, burn paper, so when you're burning paper, as you know, paper is just reacting with the oxygen in the air through combustion, and therefore it creates carbon dioxide and water. But in the process, it creates or it produces light. So production of light is one of them. Second is evolution of gas. So to the production of gas is also another indicator of a chemical change. So for example, if you have milk and or maybe any food with liquid in it, if it spoils, meaning bacteria has taken action into the food and it's now spoiled, it produces certain gases. That's why it bubbles, right? That's why spoiled food usually bubbles, and it has a different odor because it now produces those byproduct gases, right? Another one is temperature change. So when something change in temperature, usually, I mean not usually, but there's a good chance that it is involving a chemical change. Another one is change in intrinsic properties like color, odor, and other things. So, for example, when you have meat, right, or fish, raw fish, and then you cook it, cooked fish tastes different from raw fish, even without seasoning, right? Even if you don't put seasoning on it, salt or pepper or whatever, you just have raw fish and then you cook the fish, boil it or whatever, taste it. It tastes different because, again, the chemical composition is somehow changed, and that a lot of times would translate into a change in these intrinsic properties like color, odor, and other things. And then a fifth one is formation of a precipitate. So what is a precipitate first? Precipitate is a substance deposited in solid form from the reaction of two liquids. So if there is something solid formed, especially when you're dealing with two liquid reactants, that means it must be some new substance. So a cool experiment you can do at home would probably be milk and vinegar. If you have milk and vinegar, you add milk into the vinegar. Guess what? The milk curdles. So the milk is usually colloidal in form. You see some solid particles, but really close to invisible. But when you add that milk, that vinegar, the milk proteins would curdle and you have formed another substance, right? So that's what we call a precipitate. But this 5 is kind of limited because you can only see this when you have two liquid reactants. And then when you mix two liquids and then they form a solid, that is a precipitate, or not form a solid, but when you mix the two liquids, there are solid particles that settle down. That's a precipitate. So these are the 5 shall we say, evidences for a chemical change. Again, why do we need evidences? Because the way we define a chemical change is kind of atomic in nature, and it's very difficult to really see the bonds if they have been formed or not. And so we have to have a criteria that we can do at the level of our macro world. But there's a warning here, and this is very important. Take note that it doesn't mean that a chemical reaction must show all these 5 evidences. It's not a requirement, right? It's not a requirement. But not every process that exhibits one or two involves a chemical change. So it's even worse than this, because at first you would say evidences of chemical change. You might say, this is the criteria then. So therefore, every chemical change must tick off all of these five for us to say it's a chemical change. Actually, no. It could be that it would only exhibit two or three of the five listed there, and it's a chemical change. But what is even more confusing is, even if something displays one or two of them, it doesn't necessarily mean that it is already a chemical change, right? So not every chemical change will for sure involve the exhibition of one or two or three of the evidence above. So, sir, it's kind of useless then. Why do we use evidence of chemical change when it's not really a surefire way of telling if it's a chemical change or not? Well, again, we have think of it as a guideline. Think of it as a warning, a notification thing, where if something exhibits these evidence, it is possible for it to involve a chemical change, but you are still not sure. But again, um, we just list them so that it makes our lives easier, in order to determine, in order to kind of narrow down the chances. And again, science is all about possibilities. It's all about statistics, right? So you can never really be sure about anything. But that is one way of, let's say, narrowing down the possibilities, right? Because if something happens and it doesn't exhibit any of the evidences, for sure it's not a chemical change. But if it exhibits, the chances of it being a chemical change would now increase. But again, it's not a surefire way of doing that. So how what do we suggest then? This one, a more reliable way of determining is really to examine and compare the substances involved and before the change. Okay, so as the name suggests, there must be a change. So you look at what were the substances before, and then you look at what were the substances after. Did this Were we able to make a new substance? Does the products differ from the reactants or from the initial substances that you had? Because there are a lot of things that are tricky. Okay, for example, when water condenses into water droplets, so when you have water particles and then it condenses into water droplets, it changes in temperature, right? In fact, this is why how we do cooling things. We we let certain water vapor absorb the heat. I mean, we do direct the process to do like that, so that we can have a transfer of energy, and that transfer energy translates into change in temperature. So you might think that it's a chemical change, but again, if you look at the properties of water vapor, which is what we started with, and water droplets, which is what we ended up with, the products, it's still made up of water. So they did not undergo a chemical change. It was just a physical change, even if it exhibited one of the evidences of chemical change. So again, the evidence of chemical change is not a surefire way of saying that it's a chemical change. It just narrows the possibilities, right? But there are other more careful considerations. So for example, here, um, colors, taste, and odors. This is colors, taste, and odor. This is a more reliable way, because remember, colors, taste, and odors are intrinsic properties. So if the properties of the substance you start with and the properties of substance you ended up with is different, it probably means that there's something that has changed. So an example for this is when you have raw fish and cooked fish. If you have raw fish, right? Like some people eat raw fish, like sashimi or other delicacies in Japan, sushi. Um, you would notice that it tastes different when you cook it. And that's because at first you might say, this is a physical change, sir, right? Because you had fish when you started, right? And then when you cook the fish, it's still fish. So I did not change the material. So it must be a physical change. But again, it's just a language problem. It's just that raw fish has no other term. It's still called fish than cooked fish. But what is more important is the intrinsic properties. Did the intrinsic properties change? Right? So when you taste that raw sashimi or sushi versus when you cook it, did it taste different? And the answer is yes. That means the odor, that means the taste, the odor. Remember, flavor is actually taste plus some odor, right? If you did not know that already. Um, it tastes different because there were new substances formed. In fact, the uncooked proteins looks like this, and then when you cook it with heat, it will denature and it will aggregate. Denature, it's another way of saying it will unfold, right? Remember when we discussed proteins, it has three-dimensional shape. It will unfold and it will probably be cut into different places. So we call it aggregated proteins. And that's why you notice the taste is different. But mind you, those two examples are tricky because remember, when water condenses into water vapor condenses into water, it seems like it's a chemical change, but it's a physical one. And cooking meat or cooking fish seems like a physical one because it's fish, and then when you cook it, it's still fish, but it's a chemical one because again, the properties, the substances change. And for example, what the substances in the fish are the proteins, of course. And the proteins now become denatured and aggregated. And remember, meaning they unfold, they are snipped into different places, so they are not in one whole structure already. So that's a chemical change. Another tricky thing is biological chemical changes. So for example, sir, I planted a tree, a sapling, a seedling, and then 10 years after, 15 years after, it becomes this huge big tree. And then I ask myself, okay, is there a change? I started with a tree, small tree, and then it grew and became this big tree. So now, is that a chemical change or a physical change? And again, you might say, okay, I started with a tree and then it becomes a tree. If I actually eat the bark of the tree here, the bark of the tree, it still tastes the same. So for sure, it's a physical change, right? Because it did not change into another substance, right? And again, this is even more complicated because this requires that you also look at the process. Okay, so let me just read a snippet, a section of this. So, for example, a small tree can grow into a bigger tree. At first glance, it sounds like physical change because it involves it. It is a tree growing in size, meaning it did not change into something else. It is still a tree with the same intrinsic properties, only bigger. However, you have to realize that the tree adds more tree material into itself by converting water, carbon dioxide, and other minerals and glucose into eventually cellulose. And again, this goes back to our discussion about carbohydrates. Remember, when plants do photosynthesis, they create glucose, and then the glucose, they string them together, polymerizing them into a structural component called cellulose. Okay? So now when you consider the process, it becomes apparent that this process is chemical in nature because remember, it's not like the tree just expanded without adding new material into it. It added new material. And again, how did it do that? It took water, carbon dioxide, along with some minerals, and created glucose. And that glucose was strung together to form this structure called cellulose. And that became the tree material. So it's not even as simple as looking at the initial products and the initial substances and the final substances. You have to consider also what is in between, because again, if you don't consider that, again, you might fall into this trap of saying, okay, this is three material, and then it still is composed of three material, only more of them. So it must be a physical change. Obviously, I am discussing this in very simple terms so that you would understand. But the idea is that there are what we call tricky cases of physical and chemical change that you have to be aware of, right? That you have to be aware of. And it's not as simple as, and again, it's not as simple as, okay, there are evidences of chemical change and therefore it must be a chemical change. You must have a lot of consideration. Obviously, in the lower years, you were just studying evidences of chemical change because, again, we took at it at the general, we look at that at the general perspective. This time we have to be a little bit more specific, a little bit more detail, a little bit more complexity into our analysis and discussion. And therefore, this is what I wanted to show you. And again, what were the tricky cases of chemical change? Number one, I gave you an example. Water, for example, condensing. Anything that involves phase changes, it's just a physical change. And then cooking is one. That is kind of tricky. Some people say that it's people would try to think that it's physical change because after all, it's just fish. And then most biological changes, like you growing, or a tree growing, a plant growing, those are most probably be physical changes, right? So that's the idea there. So now with that in mind, you should be able to, for example, know if melting of ice cube is a physical one, if ripening of fruits, remember, taste the the unripe fruit and taste the ripe fruit. Do they taste the same? If not, then it's a chemical change. And you know, the evidences for that are change of intrinsic properties, right? This time you will answer on your own. Burning of fire, is that physical or chemical change? Sewing of clothes. So when you have pieces of textile and then you sew it into a into a piece of clothing material, is that physical or chemical change? Grilling of a piece of meat or rusting of iron, right? When iron rust, and spoiling of food. So you have to know what these things are. But again, to summarize what we have discussed, there are these things called physical and chemical change. Physical doesn't change the composition of the substance involved. Chemical changes the composition of the substances involved. And then you have evidences for chemical change. These are 5 evidences, right? And let me review that. And that is production of light, evolution of gas, temperature change, change in intrinsic properties such as color, odor, and other stuff, and formation of precipitate. But again, this is not a surefire way of doing that because there are tricky cases of chemical changes and physical changes. And what you really want to do is you look at the original substance, that's the one, and the final product, and you look at if there is a change in properties. And not even that, you have to look at the process that is happening in between. Again, when a plant grows, it still is a plant, only bigger, but you have to realize that to add more material to that plant, it had to do photosynthesis, and therefore that makes it the chemical change. Okay, so again, I know it sometimes it can be frustrating when you study complexities like this in science, when you have like already a an organized view of the world, like, okay, there's an evidence of chemical change. As long as I know, as long as I can determine the evidence for the chemical change, I know that it must be a chemical change. It's not as straightforward as that. And again, science is never straightforward as that. The main reason that a lot of people don't understand science is they don't realize that science has a lot of complexities in every single concept. And this is one of those complexities that I am trying to explain about chemical and physical changes.